Welcome back. We're starting 7.7.1 on discrete conditional distributions. So along with definition 7.7.1 that we saw in the previous video, the next example is going to serve to motivate the definition of a discrete conditional distribution, which we'll give afterwards. So example 7.7.1. Suppose that x and y are jointly distributed discrete random variables with joint probability mass function given below. So we're supposed to use definition 7.7.1 to calculate the probability that x is equal to 2 given that y is equal to 3. So definition 7.7.1 was if we had two sets A and B, then the probability of A given B is the probability of A intersect B divided by the probability of B. So what we're thinking of here is A is the event that x equals 2, and B is the event that y equals 3. So we're looking for the probability that x equals 2 given y is equal to 3. So using the definition of probability, conditional probability of events, this is the probability that x is equal to 2 and y is equal to 3 divided by the probability that y is equal to 3. Now this numerator, this and we have usually written just as a comma with probability, and that was the exact definition of the probability mass function. So that is exactly little p of 2, 3, the probability mass function here, divided by, well, this also we'd seen previously, the probability that y is equal to 3, a single one of the two random variables, that is given to us by the marginal. So by the marginal p sub y of 3, where this is the marginal mass function, of y. And these are values that we can get from the table. So the marginal function, you remember, we add up the values in the row or column in a mass function and write them in the margins. That's where the name came from. And so if we add up where y is equal to 3, we are going to get, so 0.27 is going to be the denominator of this fraction, 0.27, and the numerator is going to be, well, it's going to be where we have y is equal to 3 and x is equal to 2. I did that backwards, 2, 3, right? So that is exactly here. So that value of 0.09 is our numerator, and so if we put those in fraction form, that's 9/27 or 1/3. So let's just take a quick look here then. We've got an idea of this fraction. We're using the mass function, the joint mass function, p of x, y, and we're dividing it by the marginal function. And that turns out to be exactly the definition of the conditional distribution that we're going to give right after this example. So we're asked to do the same thing now in B for the probability that x equals 1 given that y equals 3 and x equals 3 given that y equals 3, right? X can take those three values, 1, 2, and 3. We've already done the probability that x equals 2. So we're going to do the other two possibilities, keeping y at the same 3. And then that's going to allow us to give what's called a conditional distribution of x given that y equals 3. So if we write down our similar definitions, p of x equals 1 given that y is equal to 3, well, we know that it's going to give us an analogous fraction here, which we can express directly in terms of the mass function and the marginal mass function. So that's p of 1, 3 divided by p sub y of 3, which is, well, p of 1, 3 in the table, 1, 3, x equals 1, y equals 3, that is here. And so we get 0.05 over the same 0.27. And so that is going to give us as a fraction 5/27 5/27. And lastly, the probability that x equals 3, given that y is equal to 3. Well, that is the last remaining square in the table, in that column. And so that's the probability of 3 divided by p sub y of 3. And again, using the table value 0.13 divided by 0.27, and that gives us 13/27. Now you see we've covered all 3 possibilities. Given that y is equal to 3, there's 3 possibilities that x can take, and we know what the probability is for each of them. So we've come up with a new distribution for x in a restricted column, given that y is equal to 3. And so that, we're going to say, is here values of x given that y is equal to 3. And those can take 1, 2, and 3. And then we want the probability, and the notation for it that we're going to see down below is the mass function, the probability. It's like a marginal, but we have a given of x given y is equal to 3, and then of x given that y is equal to 3. So we fill in our values here, 1/3, or let's write that all as 27 so that we can see that it all sort of lines up. 2 out of, or adds to 1. Probability, no, I got that wrong. This was 2. So let's move that over. This probability of 1 given y equals 3 is 5/27. And lastly here we had 13/27. So the notation that we would give using this, or how we would write using this notation here, is the probability of x given y is equal to 3, p sub x given y equals to 3 of 1 given y is equal to 3 is 5/27. So it's just an example of how we would use that notation. So let's go through then and read definition 7.7.2, which is based exactly on this. So let's let x and y be jointly distributed discrete random variables with joint probability mass function p of xy. Then the conditional distribution of x, given that y is equal to some value y0, has probability mass function. Here's that notation. So it's a little heavy as notation. Some books use different variants of this. Some put sort of this, but then only the x, or x given y0 or something. We're going to use the full heavy notation to remind ourselves that it is conditional in all respects. And so this is the probability mass function, p of x, and y is always this constant y0, and the marginal down below, p sub y of y0. And so this, right, if these are constants, this is a function of x. And this is over the appropriate support. So in the last example, we had the same support for x, y, and z, for x, 1, 2, and 3. But if you're restricting your values of y, your support for x may change. And so this has to be given over the appropriate support. And so what's missing here is the denominator is the marginal function with respect to y. And then we have the reverse definition, right? There's nothing special about x given y. The conditional distribution of y, given that x is a constant, x0, has mass function. And here's the analogous notation, p sub y given x equals x0 of y given x equals x0 is, and now we're plugging in a constant value for x, y is a variable, and now we have to use the marginal function for x. Again, same thing over the appropriate support, which may not be the same support as y has if it's not restricted. And again, the denominator there is p sub x of x0. That's the marginal probability mass function for x. So just a little remark. Now, once you have these distributions like we had in the previous example, if we didn't know it was conditional, it just looks like any old other distribution. So conditional distributions work like any distributions, and the mass function can be used to calculate probability of events, expected values, etc., and that we'll do in one of the next videos.